north, the California current carrying cool water south, Gulf Stream warm water north, and the North Atlantic taking that water all the way over to Western Europe. And this is the reason why Western Europe, it may be chilly up there at times, but it's not nearly as cold as the land masses at the same latitude over North America, because it has that warm ocean current carrying warm ocean water and air to that region. Again, the Benguela current in South Africa is carrying cold water to the equator. The Brazil current is carrying warm water south. The East Australian current is carrying warm water south. The Peruvian current is carrying cold water north. There's the Kuroshio and the California, as we said. And then there's one last major current in the ocean, and that's the Antarctic circumpolar current, also known as the West Drift. It travels westward around the entire globe. There's no landmass to deflect it, so it just travels around the globe. So gyres are in balance between the pressure gradient, that's the pressure gradient going down the hill, and the Coriolis effect. The pressure gradient wants to carry the water down the hill. The Coriolis effect wants to turn it to the right in the northern hemisphere, the left in the southern hemisphere, and the effect is the gyre. Of the 6 great ocean currents, 5 are gyres. And this chart shows the names and the usual direction of those major ocean currents. And you can see the powerful western boundary currents flow on the west boundaries of the ocean basin, and the eastern boundary currents in the east sides of the ocean basins. And the Gulf Stream is the largest and most powerful current in the world, and largest and most powerful western boundary current as well. All right, so western boundary currents, these are the narrow, deep, and fast currents found on the western borders of ocean basins with well-defined boundaries that are sometimes create actual eddies. Western boundary currents show move, that is, warm water poleward. It's the Gulf Stream, the Japan Kuroshio current, and the Brazilian current. And we also have eastern boundary currents. These currents are cold, shallow, and broad, and their boundaries are not very well defined. They do not create eddies. And eastern boundary currents move cold water toward the equator, like the Canary, the Benguela, and the California current. Transverse currents, that is, move east to west and west to east, and they link the eastern and western boundary currents. So to complete that gyre, you have to have something that links the eastern boundary and the western boundary currents, and those are those transverse currents. So the equatorial currents and the Antarctic circumpolar currents are the transverse currents. And then you have countercurrents and undercurrents, and countercurrents will flow opposite to the main current, and undercurrents will flow beneath the main flow, and they may be flowing with the flow or counter to the main flow. And here we have the equatorial current, which is going to be a countercurrent. That's one example of that. All right, we mentioned when we were talking about western boundary currents that sometimes they create eddies, and this is what those eddies look like, where this western boundary current in the North Atlantic is the strong Gulf Stream, and there's the west side of the current and the east side of the current. Both are very, very well defined. And as that water moves north, the cold water that's moving back down to the south sometimes gets entrained into that western boundary current, and it creates these eddies where warm water will spin off and cold water will get pulled in. And so you start out with the typical current, with the cold current moving south, the warm current moving north, and then some of that cold water gets entrained, and so you get a little pool of warm water that gets displaced, and that cold water gets pulled into the actual current, and sometimes it then gets ejected out of the eastern boundary of the current. So the western boundary of the Gulf Stream is usually distinct and marked by abrupt changes in water temperature, speed, and direction. Meanders, or these eddies, will form as the Gulf Stream leaves the U.S. coast at about Cape Hatteras, right about here. The meander can pinch off and eventually become isolated cells of warm water between the Gulf Stream and the coast. Likewise, cold cells can pinch off and become entrained in the Gulf Stream itself. The general surface circulation of the North Atlantic. So the numbers indicate the flow rates, and these this very odd Swedish word, sverdrups, the spheredrups. So one spheredrup equals 1 million cubic meters of water per second. And you can see that the Gulf Stream is 26 to 55 million cubic meters of water per second. So the spheredrup, again, that's that word, sverdrups, moves a tremendous amount of water in the Gulf Stream, and you can see there's lesser amount of waters in different currents. The unit is used to express the volume and transport in ocean currents, and it's named in honor of this Herald, who was one of the century's pioneering oceanographers. All right, the main effect of ocean currents is to transfer heat from the tropical regions to the polar regions, which generally and greatly affects climate at the mid-latitudes. The influence on weather and climate can be seen because San Diego has those cool, foggy summers. Mark Twain once said the coldest winter he ever spent was one summer in San Francisco. And of course, Washington, D.C. has hot, humid summers because of the Gulf Stream that moves just by it. And so the two main impacts of ocean currents are to transfer heat from the tropical to the polar regions and also to distribute nutrients and scatter organisms around the ocean. So we talked about San Francisco being cold. The big gyre in the North Atlantic moves that cold northern Pacific water south in the California current, that eastern boundary current, keeping California nice and cold, where the Atlantic gyre, the North Atlantic gyre, brings warm, moist water north with the Gulf Stream, keeping the eastern seaboard very warm. So these are generally the summer air circulation patterns on the east and west coast of the United States. And warm ocean currents are shown in red, and the cold ocean currents are shown in blue. And air is chill as it approaches the west coast and warm as it approaches the east coast. Wind can also cause vertical movements of ocean water. So we talked an awful lot now in the last few minutes over how wind induces horizontal movements, or these gyres, or the ocean currents. But wind can also induce vertical circulations, a vertical movement induced by wind-driven horizontal movement of water. So as the water moves horizontally across the ocean because of the wind, it can create either upwelling or downwelling. And upwelling is the upward motion of water. It brings cold, nutrient-rich water toward the surface. And downwelling is the downward motion of water, which supplies the deeper ocean with dissolved gases and nutrients. So this is what equatorial upwelling might look like. The south equatorial current, especially in the Pacific, straddles the geographic equator. Water north of the equator veers to the right, northward, and water south of the equator veers to the left, southward. So that means the surface water diverges. So if you look right at that 0-degree latitude, right in here, to the north it moves to the north, to the right, to the south it moves to the south, to the left. So the water here is diverging. Water, the mass here is moving away, so it has to be replaced. And it's replaced by this upwelling, Surface water, therefore, diverges, causing upwelling. Most of the upwelled water comes from the area above the equatorial undercurrent at about a depth of 100 meters or so. So it brings this water upward. So that's one example of how horizontal movement of water at the surface caused by wind creates a vertical movement of water at the surface. And this is another way that wind can induce upwelling. We'll talk about the California current, and wind from the north and along that California current blows north to south. It blows north to south. Well, Ekman transport turns it to the right. And as it turns it to the right, it pulls all this water here offshore. And because it's moving all this water offshore, that water has to be replaced. So it's replaced from deep below, creating upwelling. So that's coastal upwelling. In the northern hemisphere, coastal upwelling can be caused by winds from the north blowing along the west coast of the continent. Water is moved offshore by Ekman transport and is replaced by cold, deep, nutrient-laden water. In this diagram, the temperature of the ocean surface is shown is in degrees Celsius. And so what's very important about this is off the coast of California, that Ekman transport, or that offshore movement of water, brings very cold, nutrient-rich water up along the coast of California, and that's why California is well known for its, not only its kelp beds, but its small bait fish, its sardines, and its smelt, and its grunion, and different types of fish, because they come to the surface because all that nutrient-rich water is there, and of course that feeds larger and larger fish. All right, you can also get downwelling can also occur. So if the wind is blowing south along the northern hemisphere west coast for a prolonged period of time, so a south wind, you're going to get the water moving northward and therefore turning to the right, and that's going to pull water off the Atlantic or onshore, when it hits the coast, it goes down. So areas of downwelling, that's going to be warmer water, will be low in nutrients and relatively low in nutrient and biological activity at all, but it can supply the ocean with dissolved gases, meaning there's a lot of ocean atmosphere interaction where oxygen, carbon dioxide, nitrogen will dissolve into the surface of the ocean. And if this south wind creates a right turn because of Ekman current or Ekman transport, it pulls water onshore and forces water down, so that warmer water at the surface gets forced down, taking dissolved gases below. So again, a south wind creating a south current, Ekman transport forcing water toward the coast, and then downwelling occur. So winds creating horizontal movement of water, creating vertical movement of water. All right, so we're going to talk a little bit about what's known as El Nino, and of course there's also La Nina. But I'll tell you right off the bat, La Nina is kind of a something the media created. Really what we have is El Nino and then non-El Nino years. And the El Nino is tied to something called the Southern Oscillation. So sometimes El Nino is known as ENSO, which is El Nino, E-N-S-O, Southern Oscillation. So what we're looking at is a non-El Nino year. So this on the right-hand side is the normal situation across the Pacific Ocean. So what you're looking at is Pacific equatorial regions. And in the Pacific equatorial regions, because we have a northeast trade wind and a southeast trade wind, that equatorial transverse current moves from east to west. It moves from east to west. And so what that causes is air to rise off the surface in the west, because you get nice warm water over here, and sink toward the surface back in the east, because you're going to have colder water here. Remember, cold water is brought in from the north, from the south, that is, with the Peru current. California current brings cold water in from the north here. Cold water, the air sinks over that cold water. Warm water here, air rises over that warm water. And so the typical non-El Nino year has a lot of warm water piled up on the west side of the Pacific Ocean, and cloudy wet weather where we have dry weather on the east side. In an El Nino year, that is, the southern oscillation occurs, meaning the pressure patterns, this low here and this high here, they flip, and you get a little bit of a difference with the low forming sort of in the middle of the Pacific Ocean. So let's read through this. In an El Nino year, when the southern oscillation develops, the trade winds diminish and then reverse. So what happens is the trade winds that are blowing in here, they weaken and reverse, and that allows all this warm water, instead of flowing to the west, all that warm water flows back to the east. And where all the warm water in a non-El Nino year is piled up on the west side of the Pacific with cold water over here, in an El Nino year, because the trade winds flip or reverse, that's the oscillation, the winds blow back down that gradient, and you get much, much warmer water over the central equatorial Pacific Ocean. In an El Nino year, when the southern oscillation develops, the trade winds diminish and then reverse, leading to an eastward movement of warm water along the equator. That is the eastward movement right there of the warm water along the equator. The surface waters of the central and eastern Pacific therefore become warmer, and storms over land may actually increase. In a non-El Nino year, normally the air and surface water flow westward, and an upwelling of cold water occurs along the west coast of Central and South America. So this is the El Nino year, with this warm water flowing back toward the Central and Eastern Pacific, and in a non-El Nino year, where all that warm water stays back here on the west side of the Pacific Basin. This is what the kind of the periodicity, or how often those events happen. This goes back to about 1950, and we see the different El Nino years. So 1987 we had a big El Nino year, and then 1998 we had a big El Nino year. And you see that these El Nino periods may last for 3 or 4 to 7 years, and then the non-El Nino. So the equatorial Pacific goes from being warmer than normal to colder than normal, then warmer than normal, then colder than normal.